Right, so today we are going to see about how to solve the operational amplifier circuits. Right, it's not about, I'm not going to go in detail about the theory, right? There is a lecture notes which I uploaded in the Google Classroom. You can read about it. I just bit elaborative on notes and hints, right? So it's an operational amplifier, and then there are two types of amplifiers. One is the ideal operational amplifier, which is a conceptual device, right? You can use the properties to solve the circuits. And then we have the difference between ideal and practical operational amplifiers, right? So hopefully we can see these things once we came back, once you all came back to the classes, right? So now what I'm going to concentrate is how to solve the circuits containing an ideal operational amplifiers, right? It's not a practical operational amplifiers, right? So this class is all about solving operational amplifier based circuits, right? So as you can see here in this figure, operational amplifier is a 3-terminal device, right? So here you have an, an input V minus and a non-inverting input V. Oh, sorry. A non-inverting input V plus and an output V out, right? So these three are the important terminals. And of course, if you need an amplifier, you must have a supply, right? Plus VCC and VEE. And hence, you know that, right? So your V out swings between plus VCC and minus VEE, right? For the operational amplifier, for the V out is proportional to the difference between these two terminal voltages, that is V plus minus V minus, and we can use a proportionality constant A, right? A naught, which is called as the open loop gain, right? So there are 6 properties given in these lecture notes. You can read it, and then we'll concentrate on how we can solve the operational circuits containing operational amplifiers. Right, can you see? Right, so as I show you there, so you have an operational amplifier and your V out, and you will have a non-inverting terminal which is denoted by plus and an inverting terminal denoted by minus, right? The voltage at non-inverting terminal can be noted by V plus, and the voltage at the non-inverting terminal can be noted by V minus. This could be V out, or you may use VO, right? So here there are 2 golden rules, right? As you can see in the lecture notes, solving an operational amplifier involves only 2 golden rules, right? The first one, right? The voltage at this point and at this point will be always equal, which means V plus is always V minus for an ideal operational amplifier, right? It is not true for a practical operational amplifier, but if it is given that the amplifier is ideal operational amplifier, V plus is always equal to V minus, right? And the second golden rule is the current going inside the operational amplifier, or the current drawn by the operational amplifier, is always 0, right? In other words, the operational amplifier or the ideal operational amplifier does not draw any current from the external circuit, right? You can solve almost every circuit containing an operational amplifier using these two golden rules, right? The rule number 1 is V plus is always equal to V minus, and rule number 2 is I, or the current going inside the operational amplifier, is always 0, right? Now we'll see the inverting amplifier circuit, right? So here the circuit is given, right? Okay, I'll draw the circuit in the paper and I'll continue the derivation, right? Right. So the first one is non-inverting, sorry, it's an inverting amplifier. Right? So inverting amplifier, the circuit is, of course, here you have your operational amplifier. This is your VO and inverting and non-inverting terminal. Right here, you are going to connect your input, right, which is Vs, to your inverting terminal, and you will have a feedback resistance which is Rf, and this resistance is Rs, right? And you should ground the non-inverting terminal. Now, by applying golden rule number 1, right? The golden rule number 1 says the voltage at inverting and non-inverting terminals are always equal. So what is the voltage at non-inverting terminal or the plus terminal? Which is 0, right? The plus terminal is grounded. So the voltage at this point is 0. Hence, the voltage at this point will also be 0. Right now, you may have two currents, right? One is IS, the other one is IS. And of course, golden rule number 2 says there is no current going inside the operational amplifier, right? So if you apply Kirchhoff's current law at this node, right, so you can write it simply as IS plus IF equals 0. Am I right? Right. So here you can write your IS. Oh, in other words, you can write IS equals minus IF, right? Just bring it the other side of the equal sign, right? So your IS can be written as Vs minus 0, right? Minus 0. The voltage at this point is 0. So Vs minus 0 over Rs, right? Using Ohm's law, equals minus of, you can write your, oh, it's IF, right? IF as V out minus 0 over Rf, right? Just cross multiply this. So you will have your V out equals Rf over Rs, right, into minus of Vs. Am I right? So in other words, your V out equals minus Rf over Rs into Vs, right? So this is in the form of Vo equals minus Av into Vs, right? So your current gain Av equals minus of Rf over Rs, right? This minus sign indicates a 180-degree phase shift, right? For example, if your Vs is a sine signal, something like this, right? So your V out will be out of phase with the input, and that will be amplified, right? For example, if this is in the positive half cycle at the output, you will have the signal at negative half cycle, something like this, but the amplitude will be different, right? That will be scaled by a factor of Rf over Rs, right? So by changing the values of RF and RS, you can tune the voltage gain AV, right? If you can modify, if you increase the RF value, your AV going to increase. If RS is increased, your AV is reduced, right? Similarly, now we can see the non-inverting amplifier, right? You can see the circuit diagram of the non-inverting amplifier here, right? So there is a Vs here. Instead of inverting terminal, Vs is connected to the positive terminal, and you have a V out, V minus is connected in the middle of this loop, right? So the derivation is given here, and right, so yeah, after I explaining it, you can just recheck or verify it with the lecture notes. Right, so now I'll draw the circuit diagram of the non-inverting amplifier. Right, so we have the amplifier here. This is your V out, inverting terminal, non-inverting terminal. Oh, sorry, non-inverting terminal, and this is your inverting terminal. Right, so Vs and V out, you have two resistors, R1 and R2. Oops, can you see the figure? Yeah, and then this is connected here. Right, now you can see that, right? This is V out and this is grounded, right? So this R1 and R2 will act simply as a voltage divider, right? If you put the voltage at this point, V equals, right, this is grounded R1, so your V will be R2 over R1 plus R2 into V out minus 0. Am I right? Right, so minus 0, we can leave it, right? So your V equals R2 over R1 plus R2 into V out. If this voltage is V out, right, the voltage at this point will also be V. This is V means, yeah, it is short circuited, so the voltage will be V. Right, using golden rule 1, the voltage at these 2 points must be equal, right? So I can simply write Vs equals V. Right, now just put this value here, so your V will be V out into R2 over R1 plus R2 equals Vs. Am I right? So just this, bring this term the other side, so you can write your V out equals R1 plus R2 over R2 into Vs. Right now, yeah, just R2 over R2 becomes 1, so 1 plus R1 over R2 into Vs, V out. The resistors are always positive, and this value is always gives you a positive value, right? There are no negative signals, right? The minimum value of this one will be 1, right? If R2 becomes infinity and R1 becomes 0, the gain becomes 1, right? Hence, this is always greater than 1, right? And also, there are no negative signals. So, if you have a signal something like this, right, your output will be always in phase with the input but amplified, something like this, right? Positive half cycle will be positive half cycle, right? So this is your voltage gain, right? So this is in the form of V out equals AV into Vs. So your AV equals 1 plus R1 over R2. Right now, as I said here, this becomes 0 when, oh sorry, this term, the gain term becomes, right, this term becomes 1 when R2 equals infinity and R1 becomes 0, right? Which means R2 infinity means this is completely open circuited, and R1 0 means this is just short circuited, and hence the voltage gain becomes 1, right? So at this point your Vs becomes, sorry, V out becomes Vs, and this circuit, just simply this circuit, is called as a voltage follower. Right? Okay, now go to the next circuit, right? So we have seen about inverting and non-inverting amplifiers. Now go for the summing amplifier or adder circuit, right? So here you can see the circuit. There are V1, V2, V3, R1, R2, R3, RF, and V out, right? Let's see how we can share. So how we can solve this circuit. Right, so I'll draw the circuit diagram now. Right, so there are 3 resistors. Okay, I'll put n number of resistors, right? Not 3. We may have n resistors, right? All of them connected together. And then going into the operational amplifier, the inverting terminal of the operational amplifier, and the non-inverting terminal is simply grounded, right? So this is your V out. Let this be V1, V2, and Vn, right? This be R1, R2, and this be Rn, right? So you can write the current as, right, this is I1, I2, and up to the current of this one can be written as In, right? So of course there should be a feedback resistor, right? You can refer the circuit Rf. So here you have a current I, and this current is If, right? So similar to your non-inverting amplifier, the voltage at this point is 0, and the voltage at this point is also 0, right? Since the operational amplifier does not draw any current, so your I, using Kirchhoff's law, I plus If becomes 0, right? So if I simply write it, I plus If equals 0, hence I equals minus If. Now, what is your I? Right, you can simply write your I as I equals the summation of all these current. Am I right? Summation of I1 plus I2 up to In. So I can write the I as I1 plus I2 plus In. In other words, I can write I1 as V1. The voltage at this point is 0, right? If this is 0 means all this line carries 0 potential. So I1 becomes V1 minus 0 over R1, which is V1 over R1. So simply I can write this as V1 over R1 plus V2 over R2 up to Vn over Rn, right? So now apply the value for I in this equation. So and again, your IF is going to be V out minus 0 over RF. So VO over RF, right? Minus 0 will be there, right? So IF becomes V out over RF, and then substitute this one and this one in the first equation. So you can simply write it as V out over RF equals V1 over R1 plus V2 over R2 up to Vn over Rn, right? Now you can rewrite this as V out equals Rf into, I can simply write this as, sorry, Rf over R1 into V1, am I right? Plus Rf over R2 into V2, right? Up to Rf over Rn into Vn, right? So your V out becomes something like this. Now just assume that Rf equals R1 equals R2 equals Rn equals R, which means all the values are, sorry, there should be a minus, right? I completely forgot that. Right, there should be a minus because I equals, sorry, I equals minus of IF, right? So there should be a whole minus, and this one, there will be a whole minus here, right? If all of them are equal, now your V out becomes minus of V1 plus V2 plus Vn, right? Which means if all the resistance used in this circuit are equal, right? If R1, R2, Rn and Rf are equals, then your V out becomes the minus of summation of, right? I equals 1 to n Vi. Am I right? I equals 1 to n Vi with a minus, right? Hence, this circuit is called as the summing amplifier. Right? Or sometimes this is called as an inverting summer. Why? Because we have a negative sign here, right? Which means it is adding all the values, but also multiplying it with a minus. Hence, we can call this as an inverting summer. Right, so we have seen about inverting summer. Right, now we have an analog subtractor or a differential amplifier, right? I will leave this one for your practice, right? Which is simple, right? Here you have a potential divider. Here you have another potential divider, which are R1 and Rf. So you can calculate V plus and V minus. Am I right? And then based on golden rule number 1, V1, so V plus equals V minus. If you equate them, you will end up with this equation, and if you apply Rf equals R1 and R2 equals R3, you will have your V out as V2 minus V1, which is the difference between the input voltages, right? So your V out is proportional to, or V out equals to the difference between V1 and V2, right? So I'll leave this one for your practice, right? You can just refer the lecture notes or you can practice it yourself. Right now, we'll see about analog differentiator and analog integrator. Right, so for the analog differentiator, you have a capacitor here. this is just an inverting amplifier. Instead of RS, you have a capacitor. In the same circuit, if you replace your feedback resistor RF with a capacitor, that becomes analog integrator. Right? Let's see how these circuits are performing the integration and differentiation, right? Right. Now, let me draw the circuit, right? So here we have a capacitor and the amplifier and a feedback resistor. So this is your V out and this is grounded. Always these signals or these signs, the inverting and non-inverting signs are important, right? If it is not mentioned, the circuit is completely wrong, right? So this will be RF and this is C, right? This V in, right? We know by definition, current is rate of flow of charge, right? Which means I equals dq by dt. Am I right? So in a capacitor, the total charge stored in the capacitor, right? So Q equals C into V. Am I right? So by using these two, what is the current through capacitor? Instead of Q, just substitute C into V. So your current through the capacitor, let this be I in, right? I in equals d dt of C into V in. Am I right? The voltage at this point is V in and the voltage at this point is 0. Why? Because the voltage at the plus terminal is 0. Based on the golden rules, the voltage at this point is also 0. Right. Now, C is a constant, right? Capacitance C is a constant with respect to time. So your I in becomes C into d dt of V in, right? The time derivative of V in will be your I in. Now, apply the same rule, right? This be IF and the current going inside the operational amplifier is 0. So your I in plus IF becomes 0. I in plus IF is equals 0 and hence I in equals minus IF, right? So now substitute all the values there, right? So your I in will be C into d dt of V in equals minus IF equals V out minus 0 over RF, which is V out over RF, right? So if you simply write this as your V out becomes, or VO becomes, if you cross multiply with the RF, so minus C into RF into d dt of V in, right? So this is in the form of V out proportional to d dt of V in. And if C into RF equals 1, hence the V out becomes minus of d dt of V in, right? Which means your V out is the minus of the differential form of input, right? If your V in is sine omega t, your output will be, yeah, the differential form of sine omega t, right? Minus. So we'll see some questions when I'll upload a tutorial maybe this Friday, so you can practice them, right? So that's why this circuit is called as an analog differentiator, right? So your V out, or actually this circuit gives you the differentiated form of your input, and hence this circuit is called as an analog differentiator. Right. Now, we'll see about the analog integrator, right? The circuit diagram is given here, right? So here, instead of RF, right, the C and RF are interchanged, right? The C is at your feedback loop. That's all, right? Right, so I'll draw the circuit diagram now. Minus, plus, that is grounded. Here you have a resistor. This is your V in, and this is your I in, and then you have the capacitor at the feedback loop, and this is your V out or VO, right? I know I'm just struggling with V out and VO, right? You just refer the lecture notes for clear verifications, right? As we seen earlier, the current through the capacitance C can be written as D, or the IC can be written as, right, C into ddt of V in. At this case, the voltage difference across the capacitor becomes V out, right? So V out minus 0, because the voltage at this point is 0. So this is 0. So the current IF becomes, right, C into d dt of V out. Am I right? And similarly, your I in becomes V in over, let this be R, right? R, right? So if you apply Kirchhoff's current law at this node, IF plus I in equals 0. So I in equals minus IF. That's all. Now substitute the values at this one, right? So your V in over R equals minus C into D dt of V out. Now we need the equation in terms of V out. Right now, cross multiply this with dt and integrate both sides, right? Or if I put dt here and integrate both sides, so I can simply write it as integration, right? So 1 over r is a constant. I can write it in front, and then v in into dt equals minus, c is a constant, right? So c into integration d v out, right? The term d v out. So integration dv out becomes v out. So I can simply write this as v out equals, this c will be here, minus 1 over rc into v in into dt. Right? So your v out becomes minus 1 over rc into integration v in into dt. If again, if this rc terms equals 1, right? If this term becomes 1, your v out becomes simply minus integration v in into dt. That's all. So your v out is the integrated form of your v in with an extra minus sign. Right? So yeah, that's all about the operational amplifier circuits, or solving operational amplifier based circuits, right? So I'll upload a tutorial, right? Hope you all have understood how to solve different circuits, right? So I'll upload a tutorial with about 5 or 6 questions, and I'll ask the demonstrators to record the answers or model answers, or to upload it in the Google Classroom, right? So hope you all enjoyed, and any feedbacks? Have you understood, or the writings and lecture notes are clear? You can unmute your mic and talk. Yeah, Bimsara. You can unmute your mic and talk. I couldn't hear from anyone.
Yes, it's clear.
Okay, I'll just stop the recording now.